Welcome back to ScienceClic. Today, space-time rotations. We live in a geometric space, in which we can move, turn, measure lengths or angles. Each person has their own frame of reference, a unique point of view of the universe, of which we are the center, and through which we locate objects around us. Taking this person's frame of reference, for example, the car is moving. But in the driver's frame of reference, it is the person onlooking which moves. Frames of reference describe the universe from a given point of view. 3 axes are enough: left, right, up, down, forward, backward. At the beginning of the 20th century, this paradigm was turned on its head when we understood that time is actually a 4th dimension of the universe. There is a 4th axis, which must be taken into account. In this video, we will try to explain this revolution, which has since allowed scientists to unify space and time, but also the electric and magnetic fields, or momentum and energy. Let's imagine a street in which a person A is standing on the sidewalk and a person B is driving a car. The car moves forwards relative to the street, and to describe its motion, we will construct a space-time diagram. To do this, we freeze each instant and stack the images on top of one another. They thus form a block which represents the flow of time. In this block, the 2 persons move towards the future, each drawing their own world line. Person A follows a straight line towards the future, while person B, who is moving, traces a tilted path. Each slice of the diagram pinpoints their location at a given time. At this stage, the situation is described from the point of view of the road in the reference frame of person A. What would the diagram look like if we asked the driver to draw it from his point of view? In his reference frame, B is at the center of the universe. To form his diagram, we must therefore shift all slices one after the other to replace him at the center of the scene. The car is now motionless, and it is person A who seems to be moving backwards. We have just performed a Galilean transformation. Shifting the slices of space allows us to change our frame of reference. In this way, physicists understood as early as the 17th century that motion depends on the observer. For A, B is in motion, but for B, it is A who moves. Neither of these 2 statements is more valid than the other. Motion is relative. If B decides to throw a ball, the speed of the ball will seem faster for A since it is moving with the car. According to Galileo, we can add up velocities to change reference frames. While this idea may seem natural and intuitive, a discovery made at the dawn of the 20th century came to question it all. Imagine that A and B both turn on a flashlight. Neglecting the presence of the air, which slows it down, light escapes from the 2 lamps at 299,792,458 meters per second. Viewed from the road, we would expect that the ray launched by B moves slightly faster since it should add to the motion of the car. However, against all expectations, the 2 beams have exactly the same speed. With astonishment, physicists discovered that this precise speed is absolute. Any object moving at 299,792,458 meters per second will have this exact speed in all reference frames. It is called the speed of light. This finding came as a drastic shock. How is it possible that this speed does not add up to that of the car? Why, unlike the ball thrown by B earlier, does light not change speed from one frame to another? To grasp the extent of the problem, imagine that A emits one light ray on each side. In her reference frame, both rays have the same speed. But in B's reference frame, the diagram becomes slanted. For him, light should move faster in one direction than the other, and yet it remains the same. The solution to this paradox will be found at the beginning of the 20th century. For the speed of light to remain constant in accordance with observations, the diagram must be distorted by shifting not only slices of space, but also slices of time. This manipulation is the only one allowing us to change reference frame while preserving the speed of light in both directions, and without distorting either straight lines or the volumes of the diagram. We call this a Lorentz transformation. The idea behind it is shocking. Time and space warp and change direction depending on the observer. The duration between events, the order in which they occur, and even the lengths of objects become relative measurements which change from one point of view to another. These two events, for instance, occur 1 second apart in this first frame, but 1.1 seconds apart in this other frame. And the car is 4 meters long in its own frame, but slightly shorter in the frame of the road. When a body moves relative to us, its clock seems to tick in slow motion, and its length seems contracted. This is special relativity. Let's slightly digress for one moment. Viewed from above, a city can be depicted on a map that identifies the layout of its road network. If we rotate this map, the position and direction of the roads seem to change. This is just an illusion. The orientation of the map is arbitrary. It is an abstract description of the world which does not impact reality. Physicists quickly made the analogy between the space-time diagram and a map. Like a map, our diagram is only an abstract representation of the universe, and like with a map, we can change our point of view to look at it. In other words, the Lorentz transformations which allow us to switch reference frames are somewhat equivalent to the rotations of our map. This idea makes sense because, like rotations, Lorentz transformations preserve straight lines and volumes. But unlike classic rotations, Lorentz transformations seem to distort the diagram. They do not preserve distances between points. Some move away, while others get closer. And while rotations draw circles, they draw hyperbolas. How could such transformations be equivalent to rotations? The genius idea to explain this will be brought by Poincaré and Minkowski. They invented a new way of measuring distances within the diagram, the Minkowski metric. According to them, our diagram is abstract and does not faithfully represent real distances through spacetime, somewhat like a world map which deforms the surface of the Earth to make it flat. Even though it may not look like it, all the points which make up a hyperbola would actually be the same distance from the center. The hyperbola would be the analog of a circle, the curve whose points are all the same distance from the center. By changing frame of reference, all points slide along these hyperbolas while remaining at the same distance from the center. Thanks to the Minkowski metric, the analogy becomes perfect, and the Lorentz transformations are indeed analogous to rotations. They are hyperbolic rotations. Unlike a classic rotation, which can turn in all directions, a hyperbolic rotation distinguishes two types of directions. On the one hand, durations, which can be brought onto the time axis, and on the other hand, lengths, which can be brought onto the space axis. Durations and lengths are intervals of a different nature, intervals of time or of space, and light rays form a cone which separates them fundamentally. Whatever the frame of reference, a duration remains a duration, and a length remains a length. Hence, since each observer advances towards their own future, it is impossible to go back in time. We are confined within these light cones, and in all frames of reference, the future remains the future. A classic rotation always ends up looping on itself after 360 degrees. But a hyperbolic rotation can rotate indefinitely because the angle of the rotation is no longer measured along a circle but along a hyperbola which extends to infinity. We can thus rotate spacetime as much as we want. The angle of a spacetime rotation is called rapidity. It measures how fast one frame of reference moves relative to another. The rapidity of the car, for instance, is the angle between its own frame and that of the road. If the car accelerates, its rapidity increases. If it accelerates for an infinitely long time, it would end up reaching the speed of light. Thus, the speed of light actually amounts to an infinite rapidity. It is the maximum speed that an object could only reach in theory when accelerating for an infinitely long time. Light is infinitely fast. When B throws a ball, it is not its velocity or its speed which are added to that of the vehicle, but its rapidity. Thus, when B emits light, the speed of the car does not add on, since the rapidity of light is already infinite. By revealing all these concepts, physicists have gradually discovered the geometry of spacetime. Far from being an abstract diagram, spacetime is now a physical entity, endowed with distances and rotations. This new vision has allowed scientists to understand that time and space are only dimensions of a single object, spacetime. Spacetime allows us to better understand the notion of acceleration, for instance. An object is said to accelerate when its motion is altered by changing either speed or direction. In spacetime, we understand that these two cases are both rotations, a classical rotation or a hyperbolic rotation. Accelerating actually amounts to turning within spacetime. Spacetime also unifies electric and magnetic fields. An electric field generates a force which accelerates charged particles, while a magnetic field generates a force that makes them turn. These two situations are in fact analogous. Just like the magnetic field, the electric field makes particles turn, only with hyperbolic rotations within spacetime. The electric field is the time version of the magnetic field. Finally, this vision allows us to unify the notions of momentum and energy. Energy is actually the time version of momentum. While one measures movement through space, the other measures movement through time. A stationary object, for example, has no momentum. It does not move through space, but it has energy because it moves through time towards the future. If the object accelerates, its speed changes. It turns within spacetime and gains both momentum and energy. By approaching the speed of light, these two quantities tend to infinity. Lorentz transformations are only abstract rotations of our map of the universe, changes of reference frame which don't affect the true geometry of spacetime. In the years following these breakthroughs, Einstein and his contemporaries will discover that spacetime can in fact get distorted, explaining the phenomenon of gravity. The theory of general relativity is born. However, special relativity was not abandoned for all that. Just like the Earth, which is curved but seems flat on a small scale, spacetime is still adequately described on a small scale by the Minkowski metric, the basis of our understanding of the universe. Today, new theories are trying to understand this geometry at the fundamental scale. Is spacetime perfectly smooth, or rather cut up into small grains? Does it include more dimensions which could be curled up and therefore invisible at our scale? Or maybe it fluctuates with quantum agitations. Ideas and theories abound in the hope of one day achieving a fundamental understanding of the universe.